Welcome to the first lecture on point cloud registration. Today's lecture is sponsored by Guinness. I wish. If you hear me, please reach out. We have no sponsor. But for a change, we're changing to green. All right, very exciting topic. It's a very interesting problem. A lot of people work on it. I have worked on it, and it's always fun to try and solve a point cloud registration problem or any type of registration problem in perception. In this lecture, we particularly focus on a point cloud that we might receive from different types of sensors. And these sensors can be RGBD cameras. RGBD cameras are a type of depth cameras that will give us 3D points, depth of a point, as well as the familiar RGB image that we see. So for every RGB value, we have a depth value. And this one-to-one correspondence makes it very nice because ideally we get a dense depth map. In practice, there are missing values, there are noisy values. These cameras are very good for indoors. There are a few instances for outdoors, but their range is limited to usually 10 meters. In practice, maybe 5 or 6 meters. And illumination and sunlight can affect their performance significantly because they have to project light for sensing the depth. These are active sensors in terms of depth sensing. So a very popular data set. It's not very new. It's been 10 years, maybe. It's been around. It's called TUM, or TUM RGBD data set. This is from University of Munich. There's a collection of sequences of RGBD data, and this is a common benchmark for SLAM and visual odometry in this area. You see an example of image and reconstructed scene. Another newer data set is ETH3D data set. This is a SLAM and a stereo benchmark. You see, for example, this is a playground sequence. In the middle, you get the sunlight. This illumination can affect the appearance, the image, significantly, and that makes it very challenging to track, detect features if it's feature-based, or even register in the direct sense when we directly use the pixel values, which is a topic that we cover after point cloud registration. For the stereo camera, we usually have left and right images, and we come up with an algorithm to recover depth value of a pixel. It's a topic in computer vision, how to recover the depth, but if you see a scene from two different views, and if you know the relative transformation between camera lenses, in this case, just the baseline, then we can recover the depth. It can be noisy in practice. There are a lot of methods for solving this problem. One famous method is ELAS. This is a library for getting depth from a pair of images. So once you have the depth, this is effectively similar to RGBD sensing, although it's passive because you get the depth from two images as opposed to projecting infrared light. But altogether, you can think about them as depth cameras where you have color and points as measurements. So a lot of algorithms, they ignore where this point cloud comes from. You assume you have a measurement of that sort, and then you formulate your problem. Okay? You can go to their website. You can see a cool 3D registration example based on different methods. So historically, that's why in computer vision, they also call solving this problem a structure from motion. Structure from motion is very similar to SLAM. we want to recover the structure from the motion of the camera. However, in SLAM, we might use features and other measurements that are not necessarily from camera, and we might target to recover the trajectory. Although we could aim to recover the 3D reconstruction of the scene as well. So structure from motion is a little more specific, and it's referring to 3D reconstruction using cameras. This is now visualized using probably one of the methods here. You see the gap in the middle. When I choose the ground truth, you see it's complete, as much as it can be. And these disks, not 100% sure, but it must be surface, some sort of disks, surface patches that you create locally, and then the collection of that will reconstruct the surface for you. Let me close this. Another type of sensor that we see a lot is Lidar. Lidar, unlike camera, is an active sensor. It uses light beam and time of flight measurement to measure the range. So it's an active sensor. It works even if the scene is dark. It does not work with the light in the environment. And we don't have typically color, although we get something that is called intensity. And the intensity is the reflectivity of the material that the LiDAR LiDAR beam is getting reflected on. If the material is dark, it tends to absorb the light. If the material is bright, then it tends to reflect the light. So the reflectivity will be low and high, respectively. This is negatively correlated with the intensity of the pixels we see in the camera. So we have a data set here in Michigan, NCLT, University of Michigan North Campus long-term vision and LiDAR data set. You have LiDAR measurements across the campus, and I think an omnidirectional camera. The ground truth is actually constructed by taking sequences of data from different runs on different days and accumulating them into, you can see here, a giant graph that vertically you can imagine its time, right? You go different days, and then you also establish loop closures for different days, for different locations. Then they process this offline, and that generated the ground truth, the accurate trajectory that you see when it's overlaid on the Google map. So this was from Professor Eustis' lab in Perceptual Robotics Lab here in Michigan. And the data set is available online. You can download it. Another newer data set with the same flavor is collected in Korea by Professor Ian Kim's group. It's similar, but the platform is newer, maybe 5 years, 10 years difference in the time they collected the data, less than 10. And the city is different. This is Korea, so it's not like Michigan campus. So if you like to look at different style of urban areas, this is a good data set. So if you can register LiDAR point clouds, you can reconstruct the scene. So that's one good motivation. You can localize, you can track. Or at least it can be part of a perception system or a SLAM system, this point cloud tracking. So what is a registration problem? A registration problem refers to finding the geometric relationship between two sets of data. In this context, data typically comes from a sensor, such as Lidar or depth camera. It can come from remote sensing or aerial imagery. That's also possible. It can be 2D images. That's also a type of registration, image registration. But in general, we want to find the geometric constraint or relationship, and that is usually a transformation. Now, in the context of robotics, usually we receive a point cloud, and then we want to register it to maybe another point cloud from a previous time step, or maybe a map that we're tracking. So it can be point cloud to point cloud as in the sense of frame to frame, or it can be point cloud or frame to map registration. So anything is possible in this context, depending on different ideas and frameworks that you might want to build. But at the end of the day, you are registering two set of points for finding the rigid body transformation in this context. So you can categorize the algorithms in several directions. One is the resolution of the registration. Some algorithms try to find the transformation in a rough sense. It's a coarse registration problem. And these are usually good when we want to get something quickly, maybe as a prior or some rough idea to solve a problem. That does not require a very accurate registration for reconstruction. For example, for place recognition, it might be sufficient to detect it's the same place, roughly recover what's the geometric relationship of the image that you observed maybe 1 hour ago and a different view of the same area that you're observing now. What's the transformation of camera between two cameras at these two different times? Now, maybe it's 5 centimeters off. Maybe that's not a problem. There's no reason to aim for solving that in one pass of frame-to-frame registration. Fine algorithms, on the other hand, try to really get accurate reconstruction. When you visualize, you really want to points that truly supposed to match be aligned correctly. For example, if there's a wall, you don't want wall to be intersecting. It needs to be perfectly aligned. So that's the goal of fine registration algorithm. Regardless of how well they can achieve that, that's the aim in this category. Now, when you get data, there are two ideas, which was the case in filtering as well. One idea is called direct. Direct methods use raw observations. For example, particle filter could consume the point cloud from Lidar to localize. Indirect methods use features. For example, a Kalman filter needed features to localize. It was not working with a point cloud directly ray traced in the occupancy map. If you look confused, go back and try to localize using a Kalman filter with the occupancy. You can, but it's very unusual, and you need to work with features that are not very distinguishable. So when you solve data association, all the features are the same. They're just points. It's so easy to make mistakes. So in indirect method, we mean features that are ideally invariant in some sense. For example, SIFT or SERF or ORB. These features tend to have some properties such as scale invariance or rotation invariance. These properties will help us to, when we observe the same scene from different views, we detect the same features. That will assist the registration. What will be the example of a scaling? Scale invariance. Because the camera the monocular camera, when you see an image, depending how far you are, the building, for example, or car can be very small or very large. And when you extract feature, you don't want, for example, a corner of an object to depend on that scale, how far you are. At the end of the day, it's the corner of some object, you want to redetect it.
I could see what could be a feature which is rotation in range, but I could not imagine what could be a feature which is scale in range.
SIFT is scale invariant. And it's one of the most successful handcrafted features. So today, people like to learn features automatically, and that's what they try to do in deep learning. Before deep learning, the features were handcrafted, using some sequence of mathematical operation. For example, you could take the gradient, take the Laplacian of the Hessian, or some other ideas, Laplacian of the Gaussian, sorry, and some other methods to work with the direction of the gradient, the magnitude maybe, and a combination of them to detect the salient part of the image with the goal that you can reobserve it. Because if you can't reobserve it, then you do not know the association. And we will see why that's important. So local and global. Some solvers, some algorithms find a local solution. And that's what we talk about today. There are other algorithms that can solve the problem globally. But usually under certain assumptions and given setup, they can do that. And the trade-off usually is that how fast you can solve it. Some algorithms are real-time. Ideally, this should be real-time. If it's global and it's too slow, it will limit the applicability of the method for any real-time operation. So let's formalize the point cloud registration problem. We have a set of 3D points, and these points have 3 coordinates. It's in the 3D space. Every xi has 3 coordinates. The action of a rigid body, we define it to be this way, which is not new. A rigid body transformation rotates the point and then translates the point. Now, the reason I'm using dot, because the points are not in homogeneous coordinates. To just keep the notation consistent, we do this. Otherwise, you know by now that we have to work with homogeneous coordinates if we're supposed to do matrix multiplication. But ultimately, this will give us our x plus p. So the geometric constraint that we talk about it is, in fact, an element of the SE3 group, or the rotation part is an element of SO3, and the translation is just a 3D vector. So this transformation is the parameter that we want to estimate. If we know this parameter, the registration is solved. And it turns out this parameter is an element of a Lie group. It's not just a vector. When we formulate the problem, then that will be an optimization on Lie group. We define 2 point clouds. The first one is called the target point cloud. The target point cloud is considered to be in a fixed reference frame. This is a point cloud that is the fixed frame, and we want to align to it. The second point cloud, we call it the source point cloud. The source point cloud is the point cloud that we apply the transformation such that after rotating and translating its points, it is aligned to the target point cloud. Okay? And we are after this transformation. With this setup, we can talk about maybe one of the most famous algorithm in this area.
I had a quick question about the transformation that we made. So, for example, we have a robot that's getting subsequent scans, or it's collecting subsequent Lidar information. Is the task of making sure that each subsequent scan aligns with each other the same as aligning into a fixed frame, or are there subsequent things where at pose 1 I get a scan, I want to match that with the one that I get at pose 2, and then finally I want to make sure that the scans that I match together finally align with the fixed frame that I have?
The question is that are we also concerned with a sequence of registration and then making sure the trajectory is consistent? We are not. We are just talking about aligning two set of points. This can be a building block of that SLAM framework that you're describing. We are just focused on this specific module, point cloud registration.
I was going to ask if this target point cloud has to be known for ground truth or a map or something. But is there applications, I guess, where I don't know, I'm just asking if this is a localization type problem, or is it a mapping and localization type problem?
The question is if this is a localization problem or a mapping problem. That's not how we call it, but if you want to cast it in one of these two ideas, because in localization the map is given, we're after the pose. In mapping, the trajectory is given, we want to reconstruct the scene. I would say we're localizing because we're trying to find this relative motion. It is possible to get something that you call it Lidar odometry or visual odometry or RGBD odometry by accumulating the sequence of registration and rigid body transformation that we recover. But it will be odometry because there is drift. Unless every single registration you do is perfect, which is impossible in practice, it will be an odometry and needs to be combined with other techniques in the context of Islam. But because we might get odometry out of it, you could classify it in the localization category. The point clouds are given as measurements. So first idea that it's good to learn as a fundamental method that is very common in literature. So you know how it works, and when you see its variant, you know the foundations of it, you can focus on the little idea that maybe is trying to extend this method. So the main idea is that step 1, find the association between two sets of points. And step 2, given the associations, solve some sort of optimization problem to find the transformation. Now, the question for you is that why do we need to find the association? I have two sets of points. And I want to register them. There's a rigid body transformation that perhaps aligns this part with this part, maybe. Okay? Now, whether you solve for t or inverse of t is not very important.
Is it because we assume that there's a common structure or a shared structure between the 2 points, so the associations will kind of support that assumption that we made to the common structure and align points that share features between the 2?
Because there is an underlying structure here that these point clouds share. That's true. If there is no underlying shared structure, there's nothing to register, right? But why do we need to associate points with points? The association means that I want to know what is the corresponding points here in the, let's say, target point cloud with another point in the source point cloud.
Because if you're trying to solve for, say, a C3 transformation, as long as you have 3 points at least, then you can figure out the transformation matrix.
Well, the question is more basic, that do we know what corresponds to what here? The sensor is giving me a point cloud, I move, I get another point cloud. We don't. So there is no way to know what point corresponds to another set of points.
There might be some problems if the structure is symmetric. There might be some problems with association if the structure is symmetric. Like this one can happen.
Symmetry can cause problem as well. But ignoring everything here, we do not know what point corresponds to another point. Now, if you do not know that, how do you formulate a residual for the optimization to begin with? You do not know how to define a distance metric. You can only calculate the distance between two objects that you know you want to measure the distance between these two objects. The sensor will not tell you this. The sensor only gives you a point cloud. You move, you have another point cloud. Now, if you do, let's say, a nice setup, you can simulate that. If you do know the perfect correspondences between two sets of points and they have nice overlap, you can solve the problem in closed form. And that's the historical solution. It's called Horn's method. If you noun association, that will give you I'm skipping it here if you're interested. I'll describe the method outside of the lecture, but the idea is that centralize this point cloud around the mean, calculate the cross covariance matrix between the 2 point clouds. That will give you, because you have n by 3, and the other point cloud is also n by 3. So knowing the association means that you have exactly the same number of points in the source and exactly the same number of points in the target. And then you calculate, let's say, a cross covariance matrix M. It's going to be 3 by 3. Do a SVD factorization, and you can recover the rotation matrix. Once you recover the rotation, you go after recovering the translation by registering the mean. So that's historically the closed form solution. And we come to real life, we don't know the association. Then ICP came along. So 2 set of points might have different number of points. Let's say N1 and N2. So at the step that we associate these points, we search for nearest neighbors, basically, given current transformation guess. So for every point in the target, I will try to find one association, closest point. At that iteration, then that will lead to having the exact same number of points in 2 clouds, because I ignore the rest. I only keep the associated points. Given the association, then I can formulate a residual, define some distance metric, and then minimize it. And the obvious distance metric is just the Euclidean distance between 2 points. So that's why we call it iterative closest point. Now, this is not going to recover the transformation, so we iterate. We repeat this until hopefully it will converge.
So how do we determine
Very good question. How do we get the initial guess? We don't know. Rely on your engineering intuition. If you have another sensor, like IMU maybe, and odometry, you can. But if you just have the camera, identity, right? Now, a lot of time when people get results on these trajectories, because they're sequential, they use the previous registration result to initialize the next one. So you're always correcting a delta when you go forward in time. But at the very beginning, you start from the identity because you don't know the solution. So what makes it easier in practice? You can use a lot of ideas, but if you isolate the problem, it's very challenging because you do not know a good initial guess if the problem is nonlinear. So step one, apply the transformation, which in the beginning it will be the identity if you absolutely have no idea what the transformation might be. This means find the nearest neighbor index, right? Once you search, at this point you don't necessarily have the same number of points, but you find a set of associations that now, using these indices, you can have the correspondences. Then you can define the residual, and the obvious option here is to solve a least squares problem. However, least squares on SE3. That is why we had to go through it last time. The performance will be very poor if you do it on using Euler angles. And that's what you get in PCL, point cloud library. And I'll show you what's the difference. If you do it in Lie group, if you don't do it. So the sum is over associated point. Now, you find the optimal solution. Then you go back next time. This T is no longer identity, right? It's just some T1. You move the source point cloud a little based on the guess, then you solve for the nearest neighbor again. So at every time you update the transformation, this nearest neighbor set will change. So by no means it's correct initially or anytime along the way. And that's very dangerous because you might just fall into local minima. The symmetry could be a problem if there are similar parts that the point cloud can get trapped. So altogether, this works usually with the assumption that the difference between 2 point clouds is not so large. This method works. Now, in this basic version of it, we don't usually implement this version of it, right? We work with something called GICP. That's more common. But you cannot expect too much from it if the transformation is large. This is a local solver.
You said that step 2 is computing the residual. So can you say again what step 1?
Step 1, finding the association, solving the association between two set of points. This I, the set of indices. So I know later for n terms of, let's say, this residual, which points from target and source to call to evaluate this residual, right? Then I'm going to tell you a method for solving the association. Obviously, you don't want to do exhaustive search. You do? You don't. You're a computer scientist. You should. Or maybe exactly a computer scientist implement exhaustive search when they're lazy and tell other people don't do it. So how do we calculate this using the Gauss-Newton, right? We can use the Gauss-Newton method to solve this problem, or Levenbeck-Marquardt. What do we need? We just need to calculate the gradient. Do you remember the last part of the previous lecture? How do we get the gradient? It's not very difficult. Because we're dealing with rigid body transformation, there's no t plus delta t, right? It's only t exponential of delta t. Now, in the context of optimization, you're welcome to use both left and right. But stick to one. Pick one and just be consistent. Don't derive the Jacobian using left or right, and then later in your algorithm, you're integrating using the other one. That's not recommended. You might come back and say, oh, look, it's working. But it's not correct, obviously. So we can use some simple algebra to derive the Jacobian. There's no need for calculus. Perturb, it's easier to do it from the left. Perturb the transformation in the residual. What we get is the target point for a single residual term for two associated points is the target point minus the transformation times the source point cloud. Do a first order approximation of the exponential map, which is 1 plus Kc hat. And then just multiply them. The first part is the identity. You get the transformation times the source point cloud back. That will give you the residual that you see here. Whatever is left, that's supposed to be, which is here, some first order term caused by that perturbation. Right? In the same sense of Taylor expansion, you can call it a Jacobian, but here we're using a first order approximation of the exponential map. I'm also defining Z to be, for simplicity, the transformation times the source point cloud. So now this is, of course, not something we want to work with because the matrix is the variable. The known part is the vector. We should flip the order. Therefore, the Jacobian is the known part. All we need to do is find a matrix. When we multiply it by the twist as a vector, gives the same result as the left-hand side. To see what matrix will produce the same result, twist is some SO3 part, skew-symmetric matrix, and a translation part. Multiply this matrix by a vector, that the action of it will give you, of course, this, right? We have a negative sign, so it's going to be negative of phi skew times Z minus rho. Rho is the translation. Or you used to omega and V, maybe. It's the same thing. Well, you know that A skew B is negative of B skew A, right? So the negative sign will disappear here. The translation remains. And we have the Jacobian. So it's just a rearranging. And you can formalize it in state estimation book. There is an operation like this that always will solve this problem for you. You'll have a formula of going back to the Jacobian like I'm doing it. But if you don't remember, it's just a direct calculation to see what's the matrix. All right, so we have the Jacobian. You have everything to implement a Gauss-Newton algorithm. I'm seeing your confidence is leaving the room. What's the question? Which part of it is confusing?
I have a question for the direction. Because at the left-hand side of the transform matrix multiply.
Which step is confusing? No, we'll just go there and continue. The first line here?
Yeah.
Okay. So I am saying that negative of C hat times Z equals negative of phi skew rho 0, 0 times Z. Now, because I'm not working with homogeneous, I'm just defining this action to be.
But isn't that 4 by 4?
It is. That's why I defined the action of T on a 3 vector to be R, Z plus P.
So is the Jacobian 4 by 6 then?
If we would work with homogeneous coordinate, it would be, but that's just the row of zeros. It's redundant.
Okay, okay. So
Yeah,
it is.
yeah.
Okay.
Now, you can work with homogeneous coordinates, but you will get extra zeros. I am working with 3 vectors here, right? So this dot, I'm defining it to be in the same fashion as T times Z. That's why I'm not putting a dot here in R. Because R is 3 by 3, and Z is 3 by 1. So then we don't need the dot. Right? So you can just get rid of everything here. Now, just like the way you implemented the invariant Kalman filter, in your code, you can manage the calculations in different ways. Now, is it clear now? Okay. So Jacobian is, and remember, Z is T times the source point cloud, right? So the Jacobian does depend on the transformation. Each time we have to reevaluate it at every iteration. So how do we get the nearest neighbor points? A particular algorithm that is used in practice is called KD-tree. KD-tree is a data structure that partitions the space into different regions and allows you to search for nearest neighbor or query the nearest neighbor in log n as opposed to linearly searching exhaustively over all possible combinations. And linear is going up like this, right? The log is so much better. As the number of data points grows, you will see the advantage of this log n. So the library for that is called FLAN. This is a one of the common libraries. It has a very efficient implementation for fast approximate nearest neighbors. It's not exact, it's approximation, but it works very well in practice. A nice header-only library in C++ is none-of-flan, that you can get it from the GitHub page of Professor Blanco. He is the developer of MRPT, the open source C++ library for robotics. There are lots of good algorithms in that library. So this is a header-only library, so it's very easy to include it in your package, and you can just load it and use it for nearest neighbor search. Similarly, in MATLAB, Python, Julia, you can find libraries to solve this problem. If you want to read more about it, you can go to Point Cloud library. There's a documentation here. You can look into the KD3 API that they provide. So what we do, basically, you construct the KD3 using, let's say, your target point cloud, and then for every source point cloud, you have to query the closest point, or the other way around. Probably you want to construct it for your source point cloud if you're doing it in sequence, because next time your source will be maybe the target. Wait, we want to reuse it. Which one we should do? If you have frame 1, 2, 3, you have target, source, target, source, target, source. Now next time your source becomes the target, the new target, right? If they're sequential. So you can do it for both, right? But you save one of them each time. So every time you only need to construct for one of them. So let's visualize in a cartoon how this ICP is working and why it might not be the best method in practice. Imagine I have a blue point cloud. This is my fixed point cloud, and yellow is the one that I'm moving. I need to find the nearest neighbor. Geometrically, now nearest neighbor is also with respect to some distance metric. It doesn't have to be with respect to Euclidean distance, but that is, of course, the obvious choice, and that's what we do in ICP. If you go with the Euclidean distance, this blue is the nearest neighbor to all of these points. So the residual is evaluated such that all of those points get matched to that single point at this current transformation that we have. And maybe you have some other associations. So we get closer. After solving the transformation, right, we move the source point cloud. Then we solve for the association again. This time, maybe these two are getting matched, and the other two are getting matched to a single point again. We move, and you can guess the rest. So it was working, but now imagine this point cloud has 100,000 points, 10,000 points, and it's a very complicated shape. These associations are not reliable at all, the way they're getting matched. And they can guide the optimization, the search, to any direction that is impossible for us to guess. So GICP tries to make this better. There are some other algorithms in between, but I'm just moving to the milestone, something that you might implement in practice. And it is used in practice. So we want to work with a probabilistic model. Consider each range measurement from your point cloud to be noisy. Assume a tiny covariance for that point. For example, the Lidar point cloud usually have, if the Lidar is good, you might get standard deviation of 5 centimeters, something like that. A stereo camera is going to be very large. The farther you go, the point clouds can make a wave that makes everything distorted. But let's say we assume some noise distribution. And by that, we mean the actual measurement, right? Most of the time is within that covariance ellipse that the noise distribution is describing, a Gaussian noise. Now, what we want to do, we want to come up with an idea that describes the structure of the environment better. So there is an assumption that if I am registering in a room like this and there are walls, there is no need to assume that this can be a curved surface. If I know this is a flat surface, how can I geometrically describe this? So it turns out if you do the nearest neighbor search, and let's say you pick 20 nearest neighbor of a point, right? N nearest neighbor of a point. And then you can calculate the empirical covariance, the sample covariance for that point. So that point itself is the mean. And with this empirical covariance, you are describing the local shape of the point cloud, whatever that ellipse is covering. To make it flat, we need to make this covariance almost degenerate, because from 3D, it needs to become a plane. And the direction that is normal to the plane is supposed to be very small. Now, why? Because there's an assumption that there is a flat wall. Therefore, one of these eigenvalues of the covariance must be much smaller than the other ones. So, do the eigen decomposition for the covariance. This is a 3x3 diagonal matrix of eigenvalues. And set the covariance that corresponds to the normal direction to a very small value. For example, 1e minus 3, 1e minus 6. And this is the smallest eigenvalue. That's how you know it. Usually, linear algebra methods sort the eigenvalues for you. We'll go through one example code I'll show you. The first one, if that's the case, the first one is the one you want to set to a smaller value. So no matter what shape you get from the empirical covariance, you make it degenerate like this. And the effect of that is that instead of point-to-point matching, we are matching individual tiny Gaussian distribution to this Gaussian distribution in this way of making them almost flat. So as a result of that, the local shape is better described, because a point is not able, it just doesn't have the capability of describing the shape. By its very definition, it's just a point. Now, we always avoid associating this vertical wall with the horizontal wall if we can describe the structure to be this way. And that's why this is a more powerful method, right? So these covariances will slide in a way that obviously when it's vertical, the distance is large between these two covariances. And the distance will be what? A Mahalanobis distance. A weighted distance by the inverse of the covariance between two Gaussian distributions. The notation you see is usually like this, although this is not universally accepted, but in a lot of robotics and perception papers you see this. This means R transpose sigma inverse, right? So pay attention to this inverse. Sometimes people also define it using, I don't know, maybe it's an optimal control problem. They tell you this is our transpose QR. So pay attention, but be flexible. This is up to definition. So in this lecture, we defined a way to be the inverse of the covariance. So this is a weighted norm. It's no longer a Euclidean norm.
To repeat again, why GICP will still have a feature correspondence, making this kind of assumption for Gaussian algorithm? I still don't get it. Why it will provide this kind of information?
So the question is, why do we need to assume that this is a good shape? And the answer is we have no reason. That's just the choice that in a structured environment, we think that's a good idea. This is a good idea, because when you have a wall, you don't want the measurements that are coming from that wall to move in the direction orthogonal to the wall. They should just slide within that plane that they're supposed to be. This assumption is reasonable if you assume the environment is like that. If you go to unstructured environment, this assumption, it's not clear it will do so much for you, and it won't. But on roads, for example, in the city, urban area, it's still a good assumption because of the buildings and road structures.
So what are the samples of these black holes here? Because we calculate the sample covariance, right? And what are the regions considered as samples?
What are the question is, what's the region to consider for computing this empirical covariance? That depends on many things, including how much time you have for calculations. You don't want to go too far because then that will make the covariance too large. It's supposed to be a neighborhood, but if the point cloud density is not high enough, that makes it very challenging because the neighbors are far, and that creates a covariance for a large region that's not reliable. So given, I'm saying a reasonable density, but something that when visually you look at it, it describes the shape of the environment. Maybe 16, 20, 24, something like that might be a good choice. Number of points. In the KD tree, you want to query how many points you want, right? You probably also want to query within a range, not to be too far. You don't want 2 points to, you don't want 1 point to be this on this wall, on the right wall, and the other one on the left, even if they are the nearest neighbor. That's not the goal here.
So in that page, so an ICP and this one is smaller. Can you explain more how smaller this is covariance?
Can you repeat the question?
In that page.
Next page. Previous page?
Yeah, the previous page. So yeah, the very previous page. And the next one is, can you explain more how from this one to the next one?
So the covariance here is the sample covariance. We're clear on that part. We find the nearest neighbors, ignoring all the technicalities and challenges in practice. Let's say we can do it. And I am saying that we can do an eigen decomposition of find the eigenvalues of the covariance, right? Covariance is a symmetric positive semi-definite matrix. So eigenvalues are either positive or 0. In any case, you can, because it's symmetric, you can solve the eigen decomposition problem. So this lambda will be lambda 1, lambda 2, lambda 3. Now again, because there is an assumption that we are dealing with a structured environment, therefore there must be a direction that this covariance is inflated much less than the other directions, right? If the assumption is satisfied in practice. Therefore, the smallest eigenvalue will be this direction, because the eigenvalue will recover some principal directions for you, right? Then find the smallest eigenvalue and set it to even smaller to make sure it's almost flat. Make the normal direction to be almost flat. Then the covariance will shrink like this. And you can leave the other ones to 1 or something arbitrary or whatever they are. 1, obviously, depending on the scale of the problem, could mean something like meters or
So that's always corresponds to the
smallest, right? Smallest eigenvalue.
So are these distributions equivalent to the disks you showed in the second slide for the disk you shown in the second slide for the neighborhometry construction? Are these distributions the same or different?
Not exactly. The 3D reconstruction we showed with disks, those are called circles. That's a type of map representation. It's not, well, in the literature, it's independent of this context. There's no reason to tie them together. That's just defining a local patches of surface for visualization.
This is a way that we describe or we define our source points, right? So in this scenario, or at least in this figure, we don't have a target point.
We do this for both point clouds independently. We'll see it in the code.
If we're numerically calculating this covariance at every step, won't the inverse just reduce to the inverse of that window? So we can actually, this will speed it up too.
Yeah, if we're going that way, that's right. We can invert the matrix more efficiently if you want to reuse calculations. Because if you can decompose the matrix, you can just operate on the eigenvalues, right? So, now GICP has a probabilistic notion behind it. And in that sense, it's really solving a maximum likelihood problem. The residual, which is the difference between your target point minus transformed source point. First of all, we assume that each point is distributed with some I'm abusing the notation a little because I'm not using the mean here, right? This must be, of course, the mean. With some mean value and some covariance. Similarly, the source point cloud is following a mean value. The mean is just the 3D points, what you get from the point cloud. The covariance is what we just described. So for every point, we need to evaluate that. My pen doesn't write. I didn't know you can lock the tool. Okay. Stop it. Don't show me. What is going on? My finger works. All right. So the source point cloud also has I have an idea. Let's close it and open it again. It's the best idea we have in software systems so far. So similarly, the source point cloud will have a covariance. The residual is their difference. Oh, told you. Kicks me out. So the difference is, now this residual is the difference between 2 points that are normally distributed. What is the distribution of the residual? Yeah, because we can show that the mean is whatever you see the residual itself, right? It's the difference between, basically the residual is an affine function of these 2 points, right? So the mean of the residual is the target point minus t times the source point. The covariance of the residual, well, if you calculate the covariance of both sides, will be the covariance of the target point, because we assume source and target points are independent measurements. So if they're independent, it will be the covariance of the target point plus the mapped version of the covariance of the source points, because the source point is, of course, R it's not cooperating. Maybe we do need to lock it.
On drawboard, the tool lock essentially like keeps it selected throughout your writing.
I don't know what you said, but it helped me. It's fixed. I locked it too, and it's working. Thank you. So I totally misunderstood the meaning of that lock. All right, so you only know the value of a privilege when you lose it. The transformation part is something like this, and now at this point, this is very easy for us. We know that this is an affine transformation of a Gaussian distribution. It will be R sigma R transpose. And the translation part will not contribute to the covariance. So the residual of every matched point also follows an independent for the K term, right? Not all residuals are not correlated. They're independent. So every residual will have a mean, which is we see here, and a covariance, we define it as C. Now, because this is Gaussian, multivariate Gaussian distribution, which you have exponential of negative of 1/2 x minus mu transpose sigma inverse x minus mu, right? What happens if you take negative log of this? Now, if you want to maximize this likelihood, this residual distribution, which describes how likely is these 2 point clouds to be matched if the transformation is correct, it will be peaked, right? The Gaussian distribution, the distance will be small, therefore the exponential gets peaked. And that's the maximum likelihood problem in statistics. Now, but it is so much easier to work with the log of it because it will behave better when you optimize it. Because the log is monotonically increasing function, it will not change the solution of the optimization problem. Now, we don't want to maximize, usually we want to minimize. That's basically a customary thing to do. Negative to turn the maximization to the minimization. So the maximum likelihood problem for a Gaussian distribution is the same thing as the least squares problem if you take the negative log of it. So they're the same thing. The probabilistic notion of least squares is the maximum likelihood. However, maximum likelihood problem is more general. The likelihood need not to be a Gaussian distribution. If it's Gaussian distribution, it corresponds to the least squares problem. So that's why you see that we can just write all these terms. Of course, the residual is conditioned in all the given data. You can write it like that. Take the negative log of it. Ultimately, we are solving this least squares problem. The only difference is that the distance metric is changed, right? The distance metric is no longer the Euclidean distance. This is a Mahalanobis distance between 2 points. In other words, the distance is weighted by the covariance. Which the distance is calculated using this formula. So we know at this point that that's a better formulation, and this probabilistic notion helps not to trust points just based on Euclidean distance, but also taking the uncertainty and the shape around the point into account. You solve this GICP on SE3. This is a simple problem collected using a Kinect camera. You can access data. It's a MATLAB help. It's a room. You have the Kinect. You see the panda here. That the panda is fortunately reconstructed correctly. And that's how you know it's correct, right? You look at the scene. Qualitatively, you see that it's reconstructed. This is called a qualitative evaluation of the method. Quantitatively, you need to know the ground truth transformation and see what's the error. Somehow, with some metrics, you can evaluate the error. So just evaluating quantitatively might not be satisfying, because at the end of the day, you want to see what that small error means. Is it correct, or is just the number is small, but the walls are not aligned? So it's important to show both of them. So the iterative closest point is very common in robotics. That's also known as point-to-point ICP. There's a next version of that. Instead of, well, it came earlier, that's called point-to-plane. The point-to-plane assumes that around each point, you assume a flat plane and take the distance of a point to that plane instead of point-to-point. That's one level better, and it's still, sometimes we use it. Now, a lot of methods that solve the problem globally work with point-to-plane distance, because when you switch to the GICP cost function, because the covariances changes the weight of the distance changes as the transformation changes, it makes it very difficult to solve it within the context of global solvers that you see in the literature. That's why they aim for point-to-plane ICP. So generalized ICP is what we talked about. So the year is, see, these are from 90s, 2009, GICP was published. There's another class of problem called NDT, normal distribution transform. These are also interesting methods that they voxelize the whole scene. And within each voxel, there's a Gaussian distribution, normal distribution. And the overall cost function is trying to match these distributions without solving for association. So it is, when it was published, it was novel in that sense. It's trying to bypass that association part. Sometimes it works well, sometimes it does not. But this is also an interesting category of methods. Next time, I'll talk about a continuous registration method that will generalize. In theory, it's generalizing all of these methods. You can reduce it to any of them. So you have all sort of extensions. There are tons of papers that you can search. They usually build on some of these basic ideas. What are the challenges? Correspondences between 2 points, point clouds are unknown. That's a big challenge. You usually need a good initial guess to find a good local minimum. Partial and unknown overlap are also very important challenges, because when you observe a scene and move, there is a part of these 2 point clouds that they overlap. Then there is another part for each point cloud that they have nothing to do with each other. And we do not know what's the inlier process, the part that they match, and the outlier process, the part that they don't. Solving that problem can substantially improve the performance. But again, that's something that, it's a question that whether you should solve that or you should find a method that can handle it, right? So it's not clear which one we should do first. There are some recent methods, they estimate the overlap. Predator is a paper that uses deep learning to estimate the overlapping part of 2 input point clouds. But deep learning methods are usually consume smaller point clouds. They work with 1,000 points or a few thousand points. We can handle a lot more using non-deep learning methods. They use a lot of memory in deep learning, but hopefully as we go forward, we can bring both of them together and also use less memory. But also these algorithms that they don't use deep learning are general. Up to some tuning, they're general. But deep learning also relies on your training data. They're having difficulties to generalize to data sets that they haven't seen. Another challenge is that they work on a lot of data sets that are designed for computer vision challenges. Object level, an airplane, a car. This is very different from a scene that a robot is seeing. And it seems that there's a lot more work to do to extend even the most successful algorithm to the actual robot perception problems. That's unfortunate, right? Unfortunately, the best performing algorithms of computer vision leaderboards are not directly applicable to robot vision and perception problem. Sensors have limited field of view, they are noisy, and some other things that you will know if you work on the problem. So if the problem is a smaller scale and offline processing is possible, you can, of course, try many initial guesses, let the algorithm run for a long time, or you can formulate a problem to simultaneously solve for a permutation matrix that describes the association between two set of points. Ultimately, it's a reordering of two set of points so that they correspond to each other. So you can solve for a permutation matrix, which is going to be an n by n permutation matrix. N is the number of points, and the rigid body transformation. Now, you might not know, but permutation matrices form a form a discrete subgroup of SON. They're type of rotations, but they're more particular in their entries. But don't describe a continuous rotation of an object, discrete change of configuration, such as exchanging rows of matrices and columns of a matrix. That's why you have, for a permutation matrix, P transpose P is identity. This is an orthogonal matrix. A permutation matrix is always constructed from the identity matrix, right? By changing its rows and columns. A particular example of solving the problem globally is Go-ICP. This uses branch and bound method for optimization, and it is slow, but uses point-to-plane distance metric to solve the problem. And it's a coarse registration. It's not going to solve the fine registration problem for you. Okay, so if you want to put everything into an algorithm, you can write it like this. Get the initial guess, get the target point cloud and the source point cloud. While not converged, solve the nearest neighbor search, minimize the cost function, and find the optimal transformation. If the distance between the newly calculated transformation and the previous transformation is less than an epsilon, you can assume that there is no change in the transformation. You're at the local minimum. Then it's converged, and you can return it. So there are two loops. One loop is the outer loop that you see to see if there is any change in the transformation as we iterate. And of course, this optimization itself is iterating each time, right? So you have two nested loops. So this is the code that I'm giving you. I implemented this for you. And you can see that in line 8 and 9, I'm just squeezing them. I'm just getting the points, 3D points. So in line 10 and 11, I'm constructing a KD3 data structure. Don't worry about the syntax. Just think about it as some pseudocode. No, it is an actual code, but don't worry about the syntax. In line 14 and 15, for every covariance, this C is not a matrix. It's this array of covariances for every point. I'm calculating the local covariances using nearest neighbor. And my initial guess in line 18 is the identity. In line 19, I start with the initial guess. I do have some thresholds for the convergence, and I do have a maximum iteration in line 26. There is no guarantee for convergence. It might take a very long time, depending on the problem. So while not converged, and the iteration is less than the maximum number of iteration, move the source point cloud in line 31 to 34. I'm first rotating them and then translating them. Now I'm doing it all at once, right? There are a bunch of points. I'm applying a 3x3 rotation. That's why it's multiplied from the right side by transpose. Instead of writing a loop, I'm doing it all at once. In line 37, find the nearest neighbor between the target and the current source. Now, this is something that we didn't talk about it. In line 40 to 42, in ICP algorithm and GICP, when we do the nearest neighbor search, because points can be still very far from each other, we use a maximum distance threshold to remove points that the distance exceed that threshold. We consider them as outliers. The problem is, of course, what is that distance? If it's arbitrary, for every problem will be different. Which better idea is to use M estimation, as we will do. Let the robust solver ignore those instead of setting a hard threshold. Because initially the distance is large, but who knows, maybe they are inliers. We're just ignoring them because based on the current transformation guess, they are far. And that's not a good assumption. So that's why you see survived indices, not all the nearest neighbors indices. Then I'm solving a Gauss-Newton here. I'm implementing my own solver. I'm not using another library. So all I'm doing, I'm calculating the Jacobian, solving a linear system in line 54, and then integrating in line 56. Now the Jacobian is only 6 by 6 because we're only solving a system of 6 variables. Although there are many rows, but if you add them up, you can form a 6 by 6 system of equations as your normal equations, right? So the normal equations will be 6 by 6. All right, the rest is the Gauss-Newton, and then we check the distance. So for the distance, it will come up. You see that I'm taking the log of the difference between two rigid body transformations. You see the Jacobian. Line 104, this is what I derived in the slide. And this is the covariance part. For every covariance, I'm taking 6 nearest neighbor, because this is slow in MATLAB. And when I get the eigenvalue in line 121, because the eigenvalues are ordered, the first one is the smallest one. I set that to E, which is defined in line 114. Set the other one to 1, and then reconstruct the covariance using V and the new eigenvalues. Okay, so see that this algorithm, you have explicit code how you actually implement this. So what is the distance metric? We're working with rigid body transformation. The distance is, of course, one transformation times the inverse of the other one. You can take the Lie logarithm, which is the log, matrix log. If you want to see the individual rotation and translation distances, you can look into T times T2 inverse. What you will see is that the rotation is, as usual, R1 times R transpose. We take the log and then to make it a vector, and then take the norm of it. This will be a misalignment angle. However, the distance does depend on the rotation, error in the rotation. A lot of paper in the literature that tell you this, which is not correct if you're solving for rigid body transformation. But sometimes because the benchmark is giving you this, you have no choice, because you cannot compare with other methods if you don't do it, right? So you might do that, and I've done it, not proud of it, but because the benchmark is like that, you have to do it. So keep the method comparable. But the true translation distance is this one, which comes from the matrix. You just look at it, that's how it looks like. You should know this from the filtering lectures. First rotating and translating is not the same as first translating and then rotating. Now, we talked about the robust estimator that we can use, for example, the Cauchy loss function. This will add a nice property that we can softly ignore outliers instead of setting a hard threshold that everything beyond 1.5 meters should be ignored. That's too, in some sense, too conservative, even though the robust estimator is supposed to be conservative itself. So there are many options. The Cauchy loss in particular is the one that you see it's more harshly penalizing large residuals with respect to the other ones. Alpha is a value that the method start moving sublinearly, this hyperparameter alpha. So that's why we tune it to see where we want to bend this quadratic loss so that it ignores large residuals, because large residuals will have large gradient. And that will dominate all the good terms that have small residual. Okay. Do you have a question, Onur? No? So the new cost function is using a weighted distance based on local covariances. We also wrap it around an M estimator. We're really putting everything we have on the table to make sure we can fix it. And it is so much better. And we solve it on SC3. So it gives you a nice algorithm to work with. Now you can do all the association and calculations on GPU. That should make it much faster. On CPU, it might be slow for large point clouds.
Can you remind us what estimator was?
The maximum likelihood type estimator was a generalization of maximum likelihood that instead of log, we could wrap the cost function around any kernel. So the residual is, or the cost function is the norm, weighted norm of the residual, right? We wrap this around a kernel or robust function, such as this one. But what all of them they have in common that instead of no loss that moves quadratically, right, as the gradient grows, the role of this robust loss function is to, at some point, start bending the quadratic loss, because when the residual is large, in the least squares problem, we talked about it, that the gradient of the objective function is Jacobian transpose times the residual. The gradient will be very large. The outlier, by definition, does not agree with the model, this distance we're calculating. This will dominate all the good data inliers. We don't want that. This loss function helps us to ignore, reduce the effect of them, right? Instead of having this effect, it has a much smaller effect. So without making a decision, softly we're ignoring outliers, and that's very desired. As opposed to setting threshold, making a decision that I'm going to ignore this set of points in the optimization. Okay. So very quickly, there's an extension of this method that you have open source software for it. It's called Semantic ICP. If you have semantic information, how can you leverage it in this method? The idea is that if you know the labels in a point cloud, you should be able to improve the data association, because points from sidewalk should be matched with points from sidewalk. That seems to reduce the domain of association substantially if I know these labels. And these days, it is possible to get this sort of segmented point clouds. So the idea is simple. The points are labeled by their category in the scene. Therefore, if I want to move the sensor, the Lidar, and match two set of categorized or segmented point clouds, I do not need to match points that do not belong to the same category. However, and that so you see points with similar color, there's no ambiguity. These two should not be matched, right? Because they don't have the same label. However, in practice, probably the labels are not perfect. They're coming out of a softmax function that they have some probabilities. One idea that we did is that, well, let's delay the decision, use the probabilities. And what happens is that leads to an extension of this GICP to a framework that has two steps, expectation and maximization. Expectation is when we softly recover the association, instead of one-to-one, we do many-to-many. Find several points in the neighborhood that are possibly associated and weight them by their categories and information that comes from segmentation. In the maximization step, just solve the maximum likelihood problem, as usual. So EM, or expectation maximization, is a general framework, and that's what we are applying to the problem here. So what happens is that I skip the derivations here and share the paper with you. Ultimately, instead of having n terms, we have n, small n times big N, because if we are associating every residual with n other residuals, right, small n, then, for example, instead of 100 terms or 1,000 terms, suddenly we will have 5,000 terms. So it is a more expensive problem, this semantic ICP. And in the expectation part, we calculate the weight. So not every residual has the same weight, importance, especially if they don't belong to the same semantic category predicted by, let's say, a neural network. If they both come from the road, then this weight is high. If they're not, it should be very low, weighted down. And that leads to a small modification of GICP that has this expectation maximization step. Other than that, the algorithm is very similar. Now, you run this on some benchmarks like Kitty, you can see substantial improvement. This is the initial, this is the distance between the ground truth and the initial guess. And this is the distance between the final solution. You want this to not to be like this, because the final distance between the ground truth and estimated is large when it's a line. You want it to be lower. It's easier plots to understand. The CDF plot versus error. Now the GICP, when you solve it on SE3, you can see for the rotation part is doing very well, this dashed line here. For the translation, not so much yet. The other GICP, the orange one, is from point cloud library. It is using Euler angles. So with Euler angles, you get a performance that is much lower than solving on a Lie group. With the semantic ICP, you can see the translation part is also improved, which is difficult to recover if you don't know if both are from the wall, right, and there's no label, there's no reason to move them. Whereas these weights can tell you to move points even if geometrically they're similar. Okay? The semantic space has its own notion of distance, which helps to guide the transformation. Now you have the Open3D is another nice library to work with this in this area. Check these 3 links, PCL, Open3D, and the Semantic ICP and GICP SE3 are both available in C++. The implementation is available here. Some readings. And that's it for today.